Welcome to another lecture on W211. So far, we have studied all the techniques that are used to simplify and solve a given circuit. However, there are various instances where the terminal information of the circuit is only of our interest. We no longer want to redraw the circuits over and over again, and therefore there must be some technique that identifies the behavior of a given terminal in terms of the voltage and the resistance of that particular circuit. There are two very well known techniques that are widely used throughout your academic career in electrical engineering, and they are known as the Thevenin equivalent and the Norton equivalent. Both of these two equivalent circuits are actually very useful in briefcasing a given circuit or in compressing a circuit only in terms of a voltage source in series with a resistance, or for a current source in shunt with the equivalent resistance. So we shall now, in this particular circuit, we will identify how to squeeze a circuit using the Thevenin equivalent model, and how to then transform that Thevenin equivalent model in terms of a Norton equivalent model. Note that both the models, Thevenin and Norton, they are quite, once you identify one of them, then it is very much easy to actually convert them into the other form using the concept of the source transformation. Let us start with the concept of the Thevenin equivalent. Thevenin equivalent is actually a voltage which is calculated on those two terminals which are of our interest, and it is connected in series with a resistance which shows the behavior of that circuit, or which shows the equivalent resistance of the circuit seen from those two terminals. So let me first of all write down the definition of a Thevenin equivalent circuit, and then we will start with the concept of finding the equivalent circuit using the Thevenin method. So the Thevenin circuit, it is an independent voltage source known as the Thevenin with a resistance which we identify as R Thevenin in series. So for any given circuit, suppose that we have this particular circuit, and we have to find out what is the Thevenin voltage as seen on these two terminals A and B. Then the equivalent circuit shall have a this type of a shape. So we will have the V Thevenin, and this shall be the R Thevenin, and these are the two terminals A and B. Remember that the Thevenin equivalent is a very handy method of finding the terminal information behavior and to simplify a given circuit. Most of the textbooks actually have some load resistance connected across the Thevenin terminals, and it is stated that to solve the to find out the value of the current through that load resistance using the Thevenin equivalent. Whatever it is, Thevenin provides you the information, and once we have that information in available, then no matter whatever is this RL here, this is just a simple series circuit of the two resistances. However, the main trick here is to identify the value of this V Thevenin and the R Thevenin. Once we actually have these two available, then using the source transformation method, we can actually transform this in terms of the Norton equivalent method. So let me write down the definition of this Norton equivalent as well before we proceed further. Norton equivalent is an independent current source with a resistance R Thevenin in parallel. So the equivalent resistance, so the equivalent circuit here is that we shall have a current source here which is I Norton, and we have this R Thevenin. So the procedure to find out the R Thevenin is exactly the same. To have a conversion between this I Norton and the V Thevenin, we should notice that this I Norton is equal to V Thevenin divided by the R Thevenin. So whatever is the value of the Thevenin voltage and the resistance, we can actually identify this I Norton, or the amplitude value of the current source, Norton current source, that is used to define a given equivalent circuit. The R Thevenin will then simply be placed in parallel with this current source, and that constitutes the Norton equivalent circuit. Let us solve some circuits and see how we actually find the Thevenin equivalent. Let us solve an example. Suppose that we have this given circuit, and these are the two terminals A and B, across which we want to find out the equivalent Thevenin circuit. So there are two things that are required to solve this given circuit. The first thing is we need to calculate what is R Thevenin, and we need to calculate what is the V Thevenin, right? So let us see what is the procedure of finding the R Thevenin for this particular circuit. R Thevenin is, number one, we deactivate all the sources here. Remember that there is a separate technique where we have the dependent sources available. We are slowly moving towards the concept of the Thevenin equivalent circuit, and therefore this is the most simplest one. So let us first concentrate that we only have independent sources available in our circuit. So deactivating all sources means replacing a voltage source with a short circuit and a current source with an open circuit, right? Once we perform this particular thing, then the circuit will look like this one. So we have a short here, this is 5, this is 20, this 3 ampere becomes open circuit, and this is 4 ohm, this is A, and this is B. Now looking into this particular network R Thevenin, as seen from these two terminals A and B, we come to know that this 5 ohm resistance and this 20 ohm resistance, they are actually sharing the nodes, and also there is a division of current between these two branches, and therefore this R Thevenin is having this parallel combination of 5 and 20 ohm resistance, and that comes in series with this 4 ohm resistance. So the R Thevenin, looking from these two terminals A and B, it is equal to 4 plus 5 into 20 divided by 5 plus 20, and that is equal to 8 ohm. So now that we have this R Thevenin available, the second thing is to find out what is this V Thevenin for this given circuit. Remember that V Thevenin for this given circuit is actually the voltage across this it is actually the voltage across this 3 ampere current source, because the current here, this current I is equal to 0, because there is nothing connected on the terminals A and B. Therefore the voltage here is the Thevenin voltage. So let us say that V 3 ampere is equal to V Thevenin, and that is equal to V AB. So that's what we need to find in here. So to find that, let me redraw the circuit again. So we have, this is 25, this is 5, this is 20, this is 3, this is 4, and this is A, and this is B. Now we need to find out the voltage at this particular node. So this let us say this is V3, this is required. Any method that we have studied so far, be it the mesh current analysis method or the node voltage method, whatever method you like, you can apply to solve for the Thevenin voltage V Thevenin. So let us say we have applied the node voltage here using the nodal method. We have V3 minus 25 divided by 5, which is the current flowing in this particular branch. Then we have a current flowing here. We will use the same concepts that we have built so far for the node voltage method, plus V3 over 20 minus 3, because this 3 ampere is a current source and it is feeding the current into the node V3, and that is equal to 0. Now if I solve for this V3, I'll get V3 equals to 32 volt, and that is equal to the V Thevenin, or the voltage across these 2 points A and B. So now if I reconstruct this particular circuit, the Thevenin equivalent circuit is a voltage source V Thevenin, which is equal to 32 volt, in series with the resistance of 8 ohm. Here we have A and here we have terminal number B, and this is the Thevenin equivalent for this particular circuit. Now that suppose that you want to identify if you have done this correctly or not, you can always apply some load resistance across these two terminal A and B, and you can then see what is the current flowing through that particular load. If the Thevenin equivalent is calculated correctly, then the same amount of current should flow through the resistance which is connected in this original circuit, shall have the same value if it is connected across this particular Thevenin equivalent. For the Norton equivalent circuit, we shall apply the source transformation method. Source transformation method states that this voltage source, so we shall let me write this as source transformation method. It states that a voltage source in series with the resistance can be converted into a current source with that resistance in parallel, and the expression is by applying the Ohm's law. So the Norton equivalent here is that I Norton is equal to V Thevenin over R Thevenin, and that is equal to 32 divided by 8, and that is equal to 4 ampere. So the circuit shall have this particular value. This is 4 ampere. Here we have this 8 ohm resistance, and this is the terminal number A, and this is the terminal number B. So this is how we actually solve a given circuit, and we can actually elaborate a circuit containing number of components using a single voltage source in series with the equivalent resistance as seen from those two terminals. So let us move ahead and find out some to find out the Thevenin equivalent at some other circuit as well. So let us say this is example number 2. So we have a given circuit. Let us say we have this 15 ampere, then we have this is 8, this is 2, this is 12, and this is 10, and it is desired to find out the Thevenin at the two terminal A and B. The first step here is because we want to find out the Thevenin equivalent. So Thevenin equivalent requires R Thevenin and V Thevenin. Notice here that to find out the R Thevenin, we need to kill all the sources, and the procedure is to open circuit all the current sources. What we are left is these three resistances in series, and the series combination comes in parallel with this 12 ohm resistance. So we have R Thevenin, that is equal to 2 plus 8 plus 10 into 12 divided by, this is 20 plus 12, and that is equal to 7 point, that is equal to 7.5 ohm, right? So now we have the R Thevenin with us. The next important point here is to identify what is the V Thevenin here. So this is where we want to find out V Thevenin. Notice here that this 12 ohm resistance comes directly in parallel with these two terminals A and B, and therefore for this particular case the Thevenin equivalent circuit is, V Thevenin is nothing but it is equal to VAB, or the voltage across this 12 ohm resistance. So the voltage across this 12 ohm resistance can be calculated for this particular circuit using the concept of the current divider rule. So we have for this particular circuit, let me redraw this particular circuit. This is the, so the first branch is this 8, and the second branch is the sum of all these three resistance values, so that is equal to 24. So we have this 24 ohm resistance here. So the current which is flowing here, I, let us say this is I, this I is equal to that is equal to 8 into 15 divided by 8 plus 24, and this gives you the total amount of the total current which is flowing here is 3.75 ampere. Now this 3.75 ampere will create a voltage drop, or V12 is equal to 3.75 into 12, that is equal to 45 volt. So now the equivalent circuit we have is a voltage source that is equal to 45, and that comes in series with the equivalent resistance which is equal to 7.5 ohm, right? So this is the Thevenin equivalent at the terminal number A and B. So let us move ahead with some more sophisticated examples to see what happened if we actually add up the dependent sources in a given circuit. So let me draw a circuit. We have this is 3 volt, this is 20I, this is terminal number A, this is terminal number B, and the value of this resistance is equal to 25 ohm. So now we want to find out the Thevenin equivalent for this particular circuit. Notice here that this type of a circuit is usually related to the circuits where we have the transistors, right? So the transistors are actually modeled using these dependent sources. If we apply the same rules that we have studied in the previous examples, then straight away we see that there is no linkage, direct linkage between this particular circuit and this particular circuit, because there is no return path for the current between these two paths. So this means that if I straight away find out if I straight away try to apply the rules, then the R Thevenin will be should be equal to 25 ohm. However, this is not the case. This is not how we solve a circuit when we have a dependent source in it. So let us solve for this particular circuit. The first thing here is that we need to find out V Thevenin, and looking into this particular circuit, V Thevenin is equal to the voltage VAB, that is equal to the voltage across this 25 ohm resistance. So once we know what is the current flowing through this 25 ohm resistance, then we can find out what is the Thevenin voltage available, which is VAB. So let us first of all write down this particular thing. So we have V Thevenin that is equal to VAB, and that is equal to the voltage across this 25 ohm. Now because this terminal is positive and this is negative, which is the desired one for this particular numerical, so you see that we have a dependent current source which is feeding the current 20I. So the current is entering from this particular side. So according to the Ohm's law, V is equal to I into R. We have minus 20I times the total value of the resistance, which is 25. So hence we have minus 500I for which is the Thevenin. Now once we found the value of this I, we shall be able to claim the Thevenin voltage available across these two terminals A and B. Now what is this current I? I, if you closely see this particular circuit, this is actually a current controlled current source, and by definition of a dependent source is controlled by some parameter given in the same circuit. So if you see here, this I is the same current which is flowing in here. So if we want to find out what is the value of this I, then I is equal to 5 minus 3 volt divided by the resistance 2 kilo ohm here, right? So I can write this as 5 minus 3 V. What is this V here, right? So let me specify. I have forgot to specify the voltage here. This is the voltage here, right? So what is V? Minus 3 V Thevenin, because this V is exactly the same thing, which is the Thevenin voltage, which is the voltage across this 25 ohm resistance. So I can write this as 5 minus V Thevenin divided by 2000. So we have this equation number 1, and we have this equation number 2. Now if I know, because I know that this V Thevenin is actually equals to minus 500 of I, so therefore I can actually get the value of the V Thevenin here. So by using 2 and 1, my V Thevenin is equal to minus 5 volt. So this is how we can actually find out the V Thevenin. The second most important point here is to find out the R Thevenin, which is the Thevenin resistance seen from these two terminals A and B. Remember that I have earlier, a short while ago, I have actually explained that we cannot actually use the same concept of finding the R Thevenin that we have seen in the last two examples. We have to adopt a different strategy to find out what is the R Thevenin for this given circuit. So let us see how we actually proceed. So remember that for this particular circuit, if the since the ordinary methods cannot be used, so there is only one method, there is only one way through which we can actually identify the Thevenin resistance here, right? So this is plus minus V, this is 25, this is 20 times I, and this is the terminal A and B. Notice that if somehow if I measure the current here, if somehow I measure the current I here, then by using the Ohm's law, R Thevenin will be equal to V Thevenin divided by the I short circuit. So if I place a short circuit path here, let us say we have a shorted path on these two terminals A and B, and the current through that path is the I, or the I short circuit, ISC. Then by using the Ohm's law, because the Thevenin voltage is already known, I can identify the R Thevenin by having the ratio between the V Thevenin and the I short circuit current. So let us assume that there is a short circuit path here. We have this A and B are actually shorted. With this thing, let me write this thing as the procedure is as follows: that short circuit the Thevenin terminals and measure the current. Thereafter apply the Ohm's law and calculate the R Thevenin, right? So we have actually created a short circuit here. So now we have so what we have done here is, because A and B are shorted, so V is also equal to 0, right? This particular V, this is also equal to now 0. With this thing 0, this is now a short circuit path, because this is depending on this value of this V. With we have V equal to 0, so 3V is also equal to 0, which is this dependent source. Let me highlight this as well with the same color. So with this 3 volt is also equal to 0. So what we have here is that the current I now is equal to V over R, that is equal to 5 divided by 2000, right? Also, because we have a short circuit path here, this is a shorted path. So all the current flowing from this 20I shall actually flow in this particular loop. It will not go through this 25 ohm resistance. Therefore, ISC is equal to minus 20I. And what is the value of I? That we have seen in this particular equation number 3. And this is equation number 4. So using equation number 3 and equation number 4, we have ISC, that is equal to minus 50 milliampere, which means that the current is actually entering from the negative side, while it is required to find out the Thevenin equivalent with A terminal positive with respect to the B terminal. Now that we have this ISC available and we have the V Thevenin available, now the R Thevenin is equal to V Thevenin over the ISC, and that is equal to what is the V Thevenin here? So V Thevenin we have calculated earlier, V Thevenin to be equal to minus 5. So we have it here. So that is equal to minus 5 divided by minus 50 milliampere, and that is equal to 100 ohm, right? So this is equal to 100 ohm. Now I can actually draw this given circuit. This is equal to minus 5. I can write this as 100 ohm resistance, and this is A and this is B. And this is, by the way, this is the same if I have this thing. If I say this is 5 volt and I invert the terminals here, this is plus and this, and here we have the top terminal is plus and here we have the top terminal negative, and I can say this is equal to 100 ohm and this is A and this is the terminal number B. So this is how we can actually solve the R Thevenin, and we can measure the R Thevenin by actually creating a short circuit path across those two terminals, and thereafter by using the techniques that we have studied so far, we calculated what is the short circuit current through the terminals number A and B. Now because the V Thevenin is already known, the ratio of the V Thevenin and the ISC shall determine what is the value of the R Thevenin or what is the value of the Thevenin resistance. There is another method to solve for that circuit, and that is known as the concept of the test voltage. Now the concept of test voltage, let us elaborate that as well. Method number 2 for R Thevenin, and this is known as the test voltage method, or test source method is the proper name for it. In this test source method, we actually connect some test source across the output terminal, and the ratio of the value of the source with respect to the current which is supplied to the circuit required gives us the Thevenin equivalent resistance. So let us, on the same circuit, let me redraw the same circuit again, and we shall apply the concept of the test source on in this particular circuit. So for that, let me say this was the voltage. We have this is 3I, this was 2K, sorry, this is 3V, this is the current I, this was 5, and here we have 20I, this is 25, this was V, and here we were required to find out the Thevenin equivalent A and B. The procedure is as follows. Number 1, deactivate all the independent sources, right? Number 2, connect a test source across A and B terminals, right? So the circuit shall be of this following shape. So now by deactivating this particular side, we have this is 3V, this is I, here we have 20I, This is plus minus V, this is 25, and here we have, let's say we have connected a test voltage Vt here. This is the test voltage source available, and the ratio of this Vt and It shall determine what is the Thevenin resistance of this given circuit. Remember that the concept of test voltage source or a test current source is only to find out the R Thevenin of a given circuit. The procedure to find out the V Thevenin shall remain same for both the methods. So now in here, let us say we have now this particular circuit. So this IT, what is this IT? IT is equal to Vt over 25, because if we apply the Kirchhoff's current law here at this particular point, we have a current IT flowing here. It is dividing into two branches. This is I25 and this one is 20I. Because it's a current source, so it will define its value itself. So we have for here Vt over 25 shall give us the value of I25, then plus 20 of I, and that is equal to It. Also we have I is equal to minus 3 divided by 2000, minus 3V, minus 3V divided by 2000. Now this V, this particular point V, it is now equal to this test voltage source Vt. So therefore another constraint is that is equal to minus 3 Vt over 2000. Now if I put this value, let us say this is equation number 6 and this is equation number 7. If I substitute equation number 7 into equation number 6, then I get It is equal to Vt over 25 plus, sorry, this is not plus, minus 60 Vt over 2000. And from this equation number 8, I can write this as It over Vt is equal to 1 over 25 minus 6 over 200, and that is equal to 1 over 100. Then R Thevenin is equal to 100 ohm, and this gives me the same value as we calculated in the previous example. Remember that the concept of Thevenin equivalent and the Norton equivalent circuits is so important that it actually summarizes all what we have learned so far. So for a given circuit, you actually need to apply the node voltage method, or you may need to adopt for the mesh current analysis method to identify the value of the R Thevenin and the V Thevenin. And this actually encompass all the simplification techniques for resistances as well, whether they are connected in series or in parallel, the bridge network or other network. So you have to be very vigilant in identifying the value of the V Thevenin and the R Thevenin, because that is what requires the implication and implementation of all what we have learned so far. So let us move ahead. Let us move ahead and find out the Thevenin equivalent for some more circuits. Let us say we want to find out the Thevenin equivalent for this given circuit. This is 115, this is 50, this is 100, this is 65, and that's it. So we need to find out the Thevenin at this terminal number A, and this is terminal number B. Now because this circuit is very simple, so by shorting these two terminals, you can identify that which of these two comes in series and which of these two comes in parallel. So ultimately we can find out the value of the V Thevenin and the R Thevenin. Remember that for complex electrical circuits, we shall understand the concept of the spice to identify the Thevenin equivalent circuit, and that is dealt in a separate lecture. So I will try to upload the next lecture using the spice. We would like to solve the circuits using the spice, so that will be uploaded in a later class. Until then, take care. Thank you very much. Allah Hafiz.